Thank you so much for that introduction. And thank you to the International Science School for bringing me here. I'm thrilled to be in Sydney. I spent 5 years living in Melbourne, Australia, and I visited Sydney many times, and it's always great to be here. I'm traveling, and this is part of a really big trip, so I'm being very careful about a number of things. I'm wearing a mask just to keep myself safe. If you have any trouble hearing me, just let me know, and I'll figure something out with the mic. But hopefully I'm clear enough. Am I okay? Yeah, okay. Okay, great. So I'm going to be talking to you about dark matter, which is the main area of my research, and it's the thing that I'm really excited about trying to understand about the universe. So when we think of the universe, when we think of what's out there in space, we usually imagine something like this. This is a picture of the Milky Way galaxy that we live inside. And this is a wonderful view because this is a view from here in the southern hemisphere, which is where you get the best view of the Milky Way, because you can look at the center of the Milky Way. You can see that amazing bulge of the galaxy there, where there's a collection of stars and gas and dust and supermassive black hole. And this is where we live. We have something like 400 billion stars in our Milky Way galaxy. And there are galaxies all over the cosmos. This is our nearest neighbor large galaxy, the Andromeda galaxy. And if we were able to see our galaxy from the outside, it would look a lot like this. So you have the disk of the galaxy and the bulge in the center. And everywhere we look in the cosmos, we see galaxies. This is a picture from the Hubble Space Telescope. And the cool thing about this picture is that everything in this view is a galaxy, a collection of millions or billions of stars somewhere out there in the universe. Every little tiny smudge. There might be one or two stars in our galaxy kind of getting in the way. I think this one might be a star. Everything else, pretty much, every little tiny smudge is a galaxy somewhere out there in the universe. So there's amazing diversity of structures in the cosmos. This is an incredibly beautiful place, but the vast majority of what's out there is just utterly invisible. And I'm going to be talking about one aspect of the invisible universe. Today, I'm going to be talking about dark matter. And when I introduce dark matter, sometimes it's useful to use an analogy, to use something that people might have heard of, to talk about what we know about dark matter, the properties of dark matter. And one of the ones that I find works best is the Force from Star Wars. Okay, so you may or may not be familiar with Star Wars, but I'll give you an introduction to the Force. So Obi-Wan Kenobi told Luke Skywalker back in the first movie, well, the Force is what gives a Jedi his power. It's an energy field created by all living things. It surrounds us and penetrates us. It binds the galaxy together. So we can look at each one of these statements and see how they relate to dark matter. Okay, so the first one gives a Jedi his power. That is unfortunately not true. As far as we know, dark matter does not give anyone powers, and of course, not all Jedi are male, so clearly that one is incorrect. The next one, an energy field. So you can kind of think of it that way. Dark matter is some kind of matter. So matter is something that has mass. It creates a gravitational pull. But there's, of course, a connection between energy and matter, and we don't really know what dark matter is made of. It could be something that acts more like a wave than a particle. We're still kind of working that out. So I'll put like a little question mark on that one. The next one, created by all living things. Again, there doesn't seem to be a real connection between dark matter and life, except that, as far as we know, dark matter is something that made it possible for life to happen, in the sense that dark matter is something that helped matter come together in the early universe to create galaxies, to create all of the structure that we see today. So in a sense, living things would not be here if dark matter weren't there to help bring all the matter together to create things like our galaxy and the planet we live on. It doesn't affect planets per se, it affects galaxies, but you need the galaxy to create the matter to create the planet. Surrounds us, yes. So dark matter is something that forms in sort of clumps in the universe, and forms in clumps that kind of surround and that envelop galaxies. So when you look at galaxies out there in the cosmos, you have to imagine that the galaxy is a small visible part in the center of a big blob of something invisible. That invisible thing is the dark matter. As far as we can tell, just about every galaxy in the universe is embedded in a blob of dark matter, including our own galaxy. It's something invisible, it is matter, it has mass, but we don't see it, we can't touch it, but it's all around us in our galaxy. The next one, penetrates us. Yes, so dark matter has this really interesting property that it doesn't seem to interact with light, it doesn't seem to interact with electromagnetism at all. So the reason you can see things, the reason you can see me is that there is light bouncing off of me and going into your eyes. I am able to reflect light at you. I also emit light a little bit in the infrared because I'm warm, and that creates thermal radiation. And I absorb light as well. Dark matter doesn't seem to do any of those things. It doesn't seem to interact with light. It doesn't have atoms and electrons absorbing light. And because it doesn't interact with light, because it doesn't have electrons, that also kind of means it doesn't touch things. So when you touch something, what's happening is the electrons in your hand are interacting with the electrons in the object. There's two ways that they're interacting. One is just electrostatic repulsion. So just the fact that the electrons on the outside of your hand are negatively charged, and so are the things in this thing you're touching. So that creates repulsion, but that's mediated by photons, by particles of light. And if you don't interact with particles of light, you don't feel electromagnetic repulsion. But there's also the fact that the electrons in your hand are interacting through just the Pauli exclusion principle, this idea that electrons can't be in the same place at the same time at the same energy level, and that also creates a kind of feeling of solidness when you touch something. Dark matter doesn't seem to have electrons. It doesn't have something that feels those forces, and so it can pass through matter. It can pass through the entire Earth. It can pass through all of us. We think that there's about a third of the mass of a proton worth of dark matter in every cubic centimeter in this room all the time. So there's dark matter in the galaxy. We're in the galaxy. We're moving through this cloud of dark matter. It's moving through us. And the final point binds the galaxy together. Yes. So the dark matter is providing extra gravity that holds all of the stuff in the galaxy together. So there's stars moving around the galaxy, and those stars are being held in some way by the extra mass of the dark matter in which the galaxy is embedded. It helps keep the galaxy stable, and it helps hold all the stuff of the galaxy into the galaxy by providing an extra gravitational pull. So when you picture a galaxy like this, you should really imagine it inside this blob of dark matter. And that dark matter is in some sense holding all that bright matter together. So I just told you the dark matter is invisible and untouchable. So how can we see it? How do we know that it's there? Well, I like this video as an illustration of how you can tell that something weird is happening, even though you can't see exactly what's happening. So in this video, you can maybe kind of see that there's a person in the center twirling their arms around, then making that fire move around in circles. But if you can only see that the fire is moving around in circles, you already know something is happening, right? Because fire doesn't move around in circles that way. There has to be something holding it in so that as it's moving around, it doesn't just fly off and go somewhere else. And this is kind of how we know that dark matter is there. We see things that do emit light, like stars and galaxies, moving in ways that we really don't think they should without some extra force acting upon them. One of the people who helped us to understand that in the 1970s was this person, Vera Rubin. She now has a huge, amazing observatory named after her, the Vera Rubin Observatory. And she was looking at spiral galaxies, like this one. Our galaxy is a spiral galaxy. This is a particularly beautiful example of a spiral galaxy out there in the cosmos. And she was looking at how spiral galaxies rotate. So spiral galaxies do rotate, not really like this, but the stars do move around the center of the galaxy. And she was trying to understand how the stars are moving around the center of the galaxy as a way of understanding the gravity that's holding all those stars in, that's causing those stars to be able to rotate around the center. And what you expect when you look at a galaxy like this is you expect that, you know, the stars toward the outside are feeling the gravity of the central part of the galaxy a lot less. So most of the bright matter, the luminous matter, is concentrated in the galactic bulge in the center. And as you go farther out, there's just very little material in the disk. And so to a good approximation, a star close to the center just feels a lot more gravity than a star toward the outside because it's closer to where almost all of the matter is, according to what you see in the pictures. And so you would expect that very much like the solar system, the things that are closer in are moving around more quickly because they feel the gravity stronger, whereas the things that are farther out move more slowly. So you'd expect something like this. Like this is an animation of that kind of rotation where you can see in this animation the things toward the center are moving very quickly, and the things that toward the outside are moving very slowly. In much the same way that, you know, Mercury is moving around the sun much faster than Neptune because Mercury feels stronger gravity, so it has to move faster to avoid sort of falling in, right? And it can move faster without flinging itself off into space because it's got that stronger pull. But when Vera Rubin and her colleagues and others at the time were looking at the rotation of spiral galaxies, they didn't see something like this, they saw something like this. And this might be kind of a subtle thing to notice, but if you look carefully, you'll see that in the right-hand picture, the stars toward the center and the stars toward the outside are actually moving at the same speed. The ones toward the outside take longer to get around because they have farther to go, but they're moving at the same speed, which suggests that they're feeling the same amount of gravity, which is weird because they're much farther away from the center of the galaxy. In terms of a graph, this is from one of Rubin's papers. You can see that they plotted the rotational speed of the stars on the y-axis and the distance from the center on the x-axis. And what they found was that the stars toward the outside, at the very edge of the light of the galaxies, were moving just as fast as the stars toward the inside. And that's not at all what you'd expect by looking at that galaxy. What you'd expect is something like that. You'd expect what's called a Keplerian rotation curve, where the speed drops down very quickly as you get farther out from the center. It's kind of like, so what they found was basically that the stuff at the outside was just moving way too fast. There shouldn't have been enough gravity holding it in. Sort of like if you're at a playground and this big kid is pushing the merry-go-round and the little kid is sitting on the outside. If he pushes too fast, that little kid's just going to fall out into the dirt, right? Like his arms are not that strong. But if he's still holding on, if he's still sitting there and the merry-go-round's going really, really fast, he must have some kind of like invisible seatbelt holding him in, right? And here, dark matter is that invisible thing holding all those stars in so that they're not flying off into space. The idea is that dark matter is providing extra gravity, and it's holding those stars toward the outside in, even though they're moving very, very quickly, even though they should be flying off into space. So I do want to point out, though, that there is other evidence, because it's possible to get that kind of rotation curve by just altering how gravity works in the equations. And it's very frequent, actually, that you see news articles or papers where people announce, we've found a way to get galaxies to rotate quickly without dark matter being there. And it's true that you can explain the rotation of galaxies by changing the way that gravity works as a function of the distance to the edge of the galaxy. But there's a lot of other evidence that points to this same explanation that there's just extra matter. I'm going to talk about one piece of extra evidence, and it has to do with how gravity affects the shape of space. So this is a cartoon illustrating the idea of Einstein's general relativity, Einstein's theory of gravity. There are some problems with this cartoon that I'll point out, but the basic idea is that when there's a massive object, it bends the space that it's in. The main problem with this cartoon as a cartoon is that you kind of need gravity to make this cartoon make sense, right? Because why else is the thing falling down, right? So you have to really imagine this is a sort of two-dimensional analogy to what's really happening. Like if I'm a massive object in the universe, what I'm really doing is I'm pulling space in all around me in every direction. Okay, so I'm bending the space toward me as a massive object. But this is a good enough analogy just to give you an idea of the fact that massive objects bend space, okay? And because the space is bent, when something comes around and it tries to move through that space, it follows the shape of space. It moves through the bent space. So for example, if you have a massive object bending the space and a smaller object starts to move past it, it won't travel in a straight line. It'll curve around because it's following the curve of space. That's how things like orbits happen in this picture of general relativity, Einstein's theory of gravity. But it turns out that it's not just objects that follow the shape of space. Light also follows the shape of space. If you were to point a laser pointer in that direction, it also would not just go straight because it would be following the shape of space. So instead of just going straight past the object, it would follow a curved path also. So this is a phenomenon called gravitational lensing, where the path of light gets bent by the shape of space, where the space is bent by massive objects. And this is something that can show us where matter is in the universe, even if we can't see that matter. So I'm going to show you an illustration of how this works. This is a visualization made by a science fiction author who also is a mathematical physicist in his spare time. It's kind of cool. But he did an illustration of a sort of cartoon of a background of galaxies. So each of these little dots is supposed to represent a galaxy. And then a massive object moves through the picture, and that massive object bends space as it moves through, but that object is invisible. So you can only see it by the way that space is bent. And you'll see very clearly where that object is as it starts moving through. So you can see that something is happening that is moving through that field of view and bending the space that it's in. That thing that's moving through is invisible, but you can definitely see where it is because you can see that the background objects are highly distorted. And there's a few things that you notice about how those things are distorted. One thing that you'll notice is that sometimes the way that those things are distorted is you'll get multiple images of the same object as it comes through. And sometimes things will line up so that it makes kind of arcs or even a circle around that massive object. And this is something that we actually see all the time in the universe. We don't have a perfect sphere moving past like that, but we have massive objects that bend the space and create those arcs and rings and those distortions that tell us where the matter is. So a typical setup would be something like this, where there's a galaxy in the background, there's some kind of cluster of galaxies in the middle creating a big dent in space, and then there's the Earth here, and the light from that distant background galaxy gets bent around, and you get multiple images of it coming to us on the Earth. And I'll show you a couple of pictures of what that really looks like. And you'll see that it is actually a real thing. And it allows us to sort of weigh the cluster of galaxies in the center, or the galaxy that's doing the lensing. And the distortion is entirely dependent on how much matter is there, not whether that matter is visible or not. And so it's not just the visible matter, it's also the dark matter. And so we can figure out how much extra matter there is by how much lensing there is. So this is actually a picture from JWST, the newest, well, not quite the newest now, there's a newer one, but the sort of the big, exciting space telescope put out, that came out just recently. And you can see here, there's a cluster of galaxies in the center there, and you can see these arcs and these sort of distorted images along the edges. And those are things that allow us to figure out how much matter is there in that cluster of galaxies. Here's another example where you can also see this is a galaxy that was somewhere in the background, and its light has been smeared around in a very dramatic way. This is a pair of images of the same galaxy that was in the background. Here's another example where you can see some really dramatic distortions, where there's this funny-looking galaxy here that's also over here, and you get this long arc going around. And again, that tells you that you can measure how much distortion there is, and it can tell you something about how much matter is in this cluster of galaxies. And you'll find out that it's mostly dark matter. It's mostly invisible stuff. Here's an example where the alignment was really, really good. And this large galaxy here is just right in front of a distant blue galaxy in the background. And you get this thing called an Einstein ring, this almost complete circle around the galaxy. Sometimes you get a smiley face. And these images they're amazing, but they're really, really useful because they allow us to take a census of how much matter in the universe is invisible and how much it's gathered around clusters of galaxies and individual galaxies. And it really reinforces the idea that there is some invisible stuff surrounding galaxies and providing that extra gravity to hold it all together. After asking what's wrong with the microphone, you'll be asking yourself, what is dark matter? And that's an excellent question. The short answer is we really don't know. We have some ideas. We have some hypotheses. There is a sort of usual assumption that we start with, which is the idea that dark matter is some kind of weakly interacting massive particle. So what that means, the weakly part means it interacts weakly, like feebly, like a little bit, or not at all, with regular matter through the ordinary particle physics means, like bouncing off stuff. Sometimes people use this to mean it interacts via the weak nuclear force. It might do that. There are other particles that interact only via the weak nuclear force and not through electromagnetism, like neutrinos. So it may be that dark matter interacts only through the weak nuclear force. The term massive there doesn't mean that it's really heavy, it just means that it has mass. It's not massless like a photon. And then particle just means it acts like a particle. The dark matter halo, this cloud of dark matter we live in, acts like a collection of particles that interact only through gravity. This is usually abbreviated to WIMP. It's sort of a bit of a contrast with one of the early ideas about dark matter called massive compact halo objects, or MACHOs. So massive compact halo objects is massive objects like planets that live in the galactic halo. But WIMP is kind of a more, I don't know, for a long time it was like the favored model for dark matter. Now there are lots of models, and I'll talk about that. But let's start with this one. So if we assume that it is some kind of weakly interacting massive particle, then we can ask ourselves, which particle is it? And we can look to the standard model of particle physics. So this is a chart of the particles in the standard model of particle physics. I'm actually going to show this chart again in the talk in the afternoon. So I'll go through it now, and I'll go through it more quickly then. So these are all the particles that we've ever seen or interacted with or detected in a particle detector. This is actually kind of an old picture of the Standard Model. In 2012, it was updated with the Higgs boson, which was kind of the final piece of the Standard Model of particle physics as we currently understand it. So to walk through what these particles are, the Higgs boson you may have heard of. It was discovered in 2012. It's a particle that has to do with like how the other particles got mass in the early universe. It's kind of on its own in terms of its properties. So the different particles here in the purple, these are the quarks. So the quarks are particles that make up protons and neutrons. They come in different flavors. The different kinds are called flavors, and they have funny names. So there's up, down, charm, strange, top, and bottom. They were named in the 60s and 70s. There was a lot going on at the time. And then in the green, these are the leptons. So we have the neutrinos, which are these sort of ghostly particles that are produced in the sun and in other astrophysical processes, and the neutrinos pass through the Earth all the time. They're passing through you right now. You don't notice. There's billions and billions of them. And then there's the electron and the muon and tau particles, and the muon and tau are sort of heavier cousins of the electron. And the electron, as you know, is the particle that goes around the atom. When you get into more sophisticated physics, of course, it's not really going around in circles. It's kind of this cloud of electronness that surrounds the atom. It gets all quantum. But there's the electron that's part of the atom. And then in the red, these are the gauge bosons. So the gauge bosons are the force carriers. So with the photon. The photon is the particle that mediates the electromagnetic force. So it's responsible for electricity, magnetism, light. Then there's the gluon. The gluon does the strong nuclear force. It holds things together inside the nucleus, inside the proton and the neutron. And then there's the Z and W bosons, and those are responsible for things like radioactive decay. They mediate the weak nuclear force. So these are the particles of the Standard Model. So we can ask ourselves, which one is the dark matter? So we have to think about what the properties of the dark matter are. Okay, so one thing we know about dark matter is that it's massive. It has mass, right? So that rules out the massless particles here. So it can't be a photon or a gluon because those don't have mass. So take those out of the equation. Then we also know that it's long-lived. What that means is it can't be immediately decaying into some other particle because we need it to be something that's been around since the early universe and that, sort of persists in the galaxy. So that means we take away everything that has a short decay time that immediately decays into other particles. So we'll get rid of those. And then another thing that we know about the dark matter is that it has no electric charge. If it had electric charge, or if it had a significant electric charge anyway, it would interact with light and we'd be able to see it. It would bounce off stuff. It would form a disk. So we can rule out the things that have electric charge. That gets rid of the last of the quarks and the electron. And then the final piece the final thing that we can say here about dark matter is that it's slow moving. What I mean by that is that whatever the particles are, they're not like shooting relativistically through the universe. Because if they were moving really fast, they would spread out, they would diffuse more quickly, they wouldn't be able to kind of gather in clumps around galaxies. And so that rules out the neutrinos, because the neutrinos are very light and they move very fast. And we know that the neutrinos that we know about anyway can't be the entirety of the dark matter. They are, in a sense, WIMPs. They are weakly interacting massive particles. They have a little bit of mass. They interact weakly. They're particles. But they can't be all of the dark matter because they just move too fast. And there aren't enough of them if you count up how many there are. So that gives us, leads us with a conundrum, which is that none of the particles that we have ever detected that we know exist could be the dark matter, which means that we have to add something to the Standard Model of particle physics to account for whatever this is that's creating this extra gravity in galaxies. It may be that there's just one new particle, one WIMP or other kind of new particle that accounts for all of the dark matter in the universe. It may be that there's a whole sea of particles that have these properties, and there's lots of different kinds of particles, and they all collectively account for the dark matter in the universe. There might be different species of dark matter, but they all have the same properties of being massive and long-lived and slow-moving and without interaction with light. It's kind of a matter of choice, of preference, whether you think it's more extravagant to hypothesize a single new particle with these properties or a whole zoo of new particles with these properties that we can't detect. We don't know yet. So the question then is, how do we find it? There are a few ways to look for dark matter, especially if dark matter is a weakly interacting massive particle. So I'll talk about how we look for it in that, under that assumption. So, you have this problem, which is that dark matter and regular matter, generally speaking, will just pass right through each other. Right? They don't interact. But it's possible that, maybe once in every long while, even though most of the time they pass right through each other, sometimes a weak interaction can occur, and they might actually interact in some way. They might bounce off each other, they might have some interaction. And so we start with this assumption that maybe there is some kind of interaction that happens. We don't know what it looks like between the dark matter and the regular matter, and maybe that way we can learn something about what the dark matter is made of. And depending on kind of which direction we read this diagram, this cartoon diagram, we get different ways of looking for the dark matter. So if we read it sort of bottom to top, that's direct detection. So direct detection is this idea that maybe once in a while a dark matter particle will bounce off something that we can see, and we can look for that. What we would actually see if that happened is we would see a regular matter particle bounce off something that we can't see, right? It would move sort of suddenly. So a poltergeist came through and knocked something off a table, right? So we build detectors, we put them deep underground, we wait for something to come in and knock into one of the nuclei or one of the electrons that the stuff inside the detector is made of. And we have careful instruments to look at those particles and see if they move, basically. There was I have a plot from many years ago that I'll show you just because I'll show you how things have been going since then, of the possibility of interactions between stuff in detectors and dark matter. So this is a plot of, basically they have all these detectors and they see things moving in the detectors, and they can say, like, if the nucleus moved this much, it's consistent with a dark matter particle having come in and hit it with some amount of strength, right? And so you can look at where, like, how much your stuff moved and say that it's consistent with a particle of a certain mass interacting with a certain strength with that nucleus, right? And this is a very complicated plot, but what you're seeing here is the colored regions are regions where a detector saw something move in such a way that it's consistent with a particle of that mass and that interaction strength bouncing off of it. And we have several different experiments here, and they don't quite overlap, but there's kind of a sense in which maybe something's happening in this part of the plot, right? Maybe all those experiments are seeing the same kind of thing bouncing off of their detector pieces. But you also have to look at these lines. So these lines here, these are exclusion limits, meaning that there are other experiments that were just as sensitive, and they saw nothing at all. And all these exclusion limits are excluding everything in this part of the plot. They're all excluding to the upper right. So what you see is that each one of these experiments, the sort of detections in each one of these experiments is ruled out by at least one other experiment. And over the years, this is from 2013, over the years, it's just gotten worse in the sense that most of these detections have just been ruled out entirely because better data came through, more deeper experiments came through, and they found that there really wasn't anything going on there. There are a couple of places where these detections kind of persist. So there's one called the Dama detector, where it has these little spots here where maybe something really was happening there. And the Cogent detector here has a little spot there, maybe something was happening there. But they're both very strongly ruled out by other experiments. And the problem is if you keep making your detector more and more sensitive by getting to lower masses and lower strengths of interactions, you're going to run into the fact that at some point, you're going to detect all the neutrinos that are coming through. Because the neutrinos don't put a lot of energy in when they bounce off things, but they put in a little bit, and if you make your detector too sensitive, you will see all of them, and you can't shield against neutrinos. They will come through the whole Earth, they do not care. They will bounce off your detector and make it very difficult to find dark matter. So things are kind of inconclusive in terms of direct detection. There are a couple other things we can look for. We can read the diagram in another direction, this way, and look for the possibility that dark matter particles come together, annihilate, and create regular matter that comes out the other end. It's called dark matter annihilation. The idea is that the dark matter particles come in, they annihilate, they turn into regular matter, and what we would actually see is high energy particles just appearing unexpectedly. And so what we do is we look at parts of the universe where we know there's a lot of dark matter, and we ask ourselves, is there some extra radiation or extra high energy particles coming from there that might be associated with that dark matter doing annihilation? And one of the places that we look is the center of the galaxy, because we know that the dark matter is most dense in the very center of the galaxy. And we actually do see extra radiation there. This is a plot of showing the gamma rays in the disk of the galaxy, and a little zoom in. This is showing that there's extra gamma rays right in the middle of the galaxy, right in the center, right where you would expect them to be if dark matter is annihilating there. However, we don't really know what's making that extra radiation. The problem with indirect detection is that you have to understand all of the other astrophysics that's happening to be able to rule it out and say that dark matter is the thing making that extra radiation. And the center of the galaxy is a very complicated place. It has a lot of gas and dust and stars. It has magnetic fields. It has a supermassive black hole. There's just a lot going on. And in order to see it, we have to look through all of the stuff in between us and there. And so it's a complicated observation to make. We don't know for sure that it's dark matter making that. There could be like a bunch of pulsars creating radiation that we see as gamma rays. So there's one more thing we can do. We can say, well, if dark matter annihilates to create regular matter, then it stands to reason that regular matter should be able to come together and create dark matter. And so if you look at the diagram in a different direction, you can look for production. You can try to smash regular matter together and hope to create dark matter in that process. And what you would actually see then is regular matter coming together and disappearing. And so what you do is you take a particle collider, you smash your protons together, you count up all the debris of the stuff that comes out at the other end, and you hope that the amount of stuff that you see at the end is less than the energy that you put in. And maybe that missing energy is some dark matter that was created in the process and escaped because your detectors couldn't see it. Unfortunately, we haven't seen that yet, so I don't even have sort of preliminary results to show you there. We just haven't seen that happen. They're still looking at creative ways to look for missing energy signatures at places like the Large Hadron Collider, but we don't have it yet. So let's look at where we stand. So with direct detection, the results are inconclusive. There have been a few experiments that have maybe seen something, but they've been ruled out by other experiments, so we don't really know what to do with that. There's indirect detection, which is also inconclusive because we've seen a few places where there's a little bit of extra energy, but we can't really say for sure that that's dark matter annihilation happening. There's production, where we just don't have a signal yet. And then there's astrophysical evidence, things like gravitational lensing, like the rotation of galaxies, a whole bunch of other things that I didn't even get into, having to do with clusters of galaxies and the abundance of elements in the large-scale structure of the universe. And that evidence is very strong. We're really sure something is happening. So when we try and figure out what dark matter is we're really open to a lot of ideas. And so there's been this kind of blossoming of theories about dark matter in the last few years, looking at lots of different possibilities for what dark matter might be. There's the whole, WIMP idea that's kind of in the green over here. These are ideas in the sort of WIMP scenario. But there's a lot of other possibilities people have been talking about. Things like primordial black holes are very popular these days. Things like different kinds of neutrinos as the possible explanation for dark matter, neutrinos that we haven't seen yet. There's things like axion-like particles, which are sort of weird particles that act more like waves than like particles because they're so small. And then there's even people still working on things like modifying gravity to try to fix these problems. So there's good reasons to pursue this question, try to figure out what dark matter is, and I'll show you why I think this is a really exciting thing to work on by showing you like what we think the universe is made of altogether. So we can actually figure out more or less what the universe is made of in terms of the large picture of that. And we think that a full, almost 27% of the universe is made of dark matter. Most of the matter in the universe is this invisible stuff, whatever it is. Something like 80 to 85% of the matter in the universe is dark matter, this invisible stuff. We also think that most of the rest of the universe is something called dark energy, which I haven't really talked about here, but I will talk about in the afternoon. Dark energy is something that makes the universe expand faster. We don't know what that is either. And then there's just this little 5% slice that I've labeled atoms. And that's everything we've ever seen or touched or interacted with. That's the entire standard model of particle physics. Everything we really understand in the universe is in that little 5% slice. And so if we are able to understand dark matter, not only are we massively increasing the amount of the universe that we understand, we're also necessarily going beyond the standard model of particle physics. We're extending our understanding of how physics works, of how particle physics works, of what the fundamental building blocks of the universe are. And so it's a tremendously exciting field to work in because it gives us this ability to understand not just more of the universe in terms of what's out there, but more of the fundamental physics of the universe and how it ultimately works. So I'll stop there and I can take questions. Thank you.